So today I'm going to go through 3.2.1.3, which is particles, antiparticles, and photons. So to start off with, there are a load of stuff called particles. They're what makes up matter. We've got protons and neutrons. They're baryons. They're actually made up of particles called quarks. We've then got electrons. They're fundamental particles. Neutrinos, a load of other stuff. All particle has an antimatter particle. Most of them are just given really boring names. So, for example, the antiparticle for a proton is an antiproton. The antiparticle for a neutron is an antineutron. The antiparticle for the neutrino is an antineutrino. Normally, we talk about neutrinos in terms of lepton number. So you might have an anti-electron neutrino, an anti-tau neutrino. But in general, neutrinos and antineutrinos. The only one that's different, because it was one of the first ones to be discovered, is the electron. The antiparticle for the electron is the positron. We don't use the term anti-electron. Now, all the antiparticles have exactly the same mass as the particles, but they have opposite charges. The rest energy of them, so when we talk about energy of particles, we have to build into the fact that they could have energy because of their excited state, or they could have energy because they're just moving very fast as well. So the rest energy refers to a stationary particle, and it's how much energy there is in the mass. You don't do it in this part of the course, but Einstein's famous equation E equals mc squared kind of explains to us that if you have mass, you also have energy. If you have energy, you have mass. They're interchangeable. And so if we're talking about the mass of a proton, we can talk about it in grams, or we can talk about it in terms of the energy. Now, the other thing that's a bit confusing is we don't use joules for these energies, we use mega electron volts. Joules would give us ridiculously tiny values, really difficult to work with, so we talk about it in mega electron volts, where 1 electron volt is the energy that an electron gains when it's accelerated through a potential difference of 1 volt. But that's something that you do later when you do electric fields. So for now, we just say that 1 electron volt is 1.6 times 10 to minus 19 joules. That's the charge on an electron, the magnitude of the charge on an electron. So a mega electron volt, because mega is the times 10 to the 6, it's just 1.6 times 10 to minus 13 joules if you need to convert it, which you do when you talk about photons. So as well as these particles that are made of solid matter, there are also these things called photons. Photons are what is currently coming out of the phone or laptops into your eyes, and photons are short bursts or packets of electromagnetic radiation, kind of like little wavelets or whatever you like to think of them as that usually is created when an electron drops down an orbital level. It will release this energy as a little electromagnetic radiation, but there are other ways of creating photons as well. It's a model of electromagnetic radiation, and it's kind of like what we use to get around wave-particle duality, where we see that photons behave as waves and particles. Now, the energy that a photon has is given by this equation. E energy, measured in joules, is equal to h times the frequency. The frequency is measured in hertz, which is seconds to the minus 1. And h is Planck's constant. It's called the Planck constant, and it's given on the data sheet. In general, if there's a symbol you don't know, check the data sheet, because a lot of them are given on the data sheet as constants. H is the Planck's constant. It's 6.63 times 10 to minus 34. We can figure out the units by looking at the units involved in the other equations. So if we were to rearrange this, we would get H will be E divided by the energy divided by the frequency. So the units for this, we've got joules divided by seconds to the minus 1. If we're dividing by seconds to the minus 1, that's the same as multiplying by seconds. So the units of Planck's constant is joules seconds. Right, so we put this stuff together, and you find that because energy can be transferred between matter and also these kind of photons with the electromagnetic energy, you get two kind of phenomenon that have been seen to occur. Annihilation, that's when a particle meets its antiparticle. So, for example, a proton meeting an antiproton or an electron meeting a positron, they will be attracted to each other because they have opposite charge. And if they actually meet, they undergo a process called annihilation, where they disappear, the energy, the mass that makes up the particles disappear and turns into 2 photons. So you can work out the energy of the photons by working out the energies from the rest energies, converting them into joules, then working out the energies of the particle-antiparticle pair, and then you can work out the frequency of the 2 photons. You kind of like have to double it here and then halve it there, which is a bit frustrating, but that's what AQA seemed to like you to do. All you need to remember is there's 2 photons that need to be produced in order to conserve momentum. You can't have two things colliding and then only producing one thing, because momentum would be violated. The opposite, I guess, of annihilation is pair production. This time though, it's only one photon that produces a particle-antiparticle pair. So the particle-antiparticle pair can conserve the momentum, and the photon has to have enough energy, using E equals hf, to account for the rest energy of the particle and antiparticle pair. So one photon will produce energy, that energy is going to halve to produce an antiparticle pair, or rather that will produce the minimum energy for the antiparticle-particle pair, because they have to actually have kinetic energy, otherwise they're most likely going to annihilate it again. So if you have excess energy in the photon, you just get two particles produced with a lot more energy in kinetic energy. That is it for this nice little one.